So the chapter 18 homework is due on Monday, the 8th. The chapter 18 quiz will be on Monday, the 8th in lecture, because the next SI after we finish chapter 18 is either today, not a great time for the quiz, or next week, right before the test. So the test will be on chapter 16, 17, and 18. It'll be on Wednesday, the 10th. And that reminds me, I gotta get all the tests printed up and organized and stuff. And make sure you turn in any labs you haven't turned in. You turn it in class or in my office. And if you need to make up anything, you can come in next Monday. Do that. I think you can just finish all the labs for everybody. So continuing on, having fixed some factoring. So several 100,000 galaxies have been identified. Astronomers estimate there's around 60 billion galaxies in the universe, and in order of abundance, the most common are elliptical galaxies. This is just, little round balls are sort of a natural thing. They're less structured in some ways. For some reason, barred spiral galaxies outnumber normal spiral galaxies about 2 to 1. But since we don't yet understand why the bars form, we really don't understand why they're more common. So, but about 2/3 of spirals have bars. Irregular galaxies comprise of only about 1/3 of the galaxies, because irregular galaxies are sort of usually galaxies that have just collided or something like that. And when we look far into the past, irregular galaxies become a lot more common when there were a lot more galaxy collisions, because the universe is smaller. So the nearest galaxy to the Milky Way is the Sagittarius dwarf galaxy. It's on the opposite side of the Milky Way from us. It's at a distance of about 50,000 light years from the center of the Milky Way. The Milky Way has a radius of around 50,000 light years. So, it's really quite close. But and it has passed through the planet of the galaxy in the past. There's evidence of that. It was discovered in 1994. It's a small elliptical galaxy. It's being pulled into the gravity of the Milky Way. It will eventually get torn apart and become part of the Milky Way. The second nearest galaxy is the Large Magellanic Cloud at about 160,000 light years. The Small Magellanic Cloud is the third closest at about 200,000 light years. And the nearest big galaxy is the Andromeda Galaxy at about 2.2 million light years from the Milky Way, and on a collision course with us in a few billion years. So our local group of galaxies is about 50 odd galaxies, built around 3 large spirals, the Milky Way, Andromeda, and M33. So the Milky Way is a barred spiral galaxy. It's called the Milky Way because when you look at the plane of the galaxy, the stars are so dense it looks like a sort of continuous broad band that looks sort of like spilled milk. So the broad band we observe is a view into the plane of the galactic disk, and although the unaided eye can distinguish about 6,000 stars in the Milky Way, astronomers estimate there's around 100 to 200 billion. So here are some rough face-on and edge-on views of our galaxy. This is the best artist rendition because the bar is not super clear. We're about 28,000 light years from the center. So we're about halfway to the edge from the nuclear bulge. And it's about 20,000 light years thick. and 100,000 light years in diameter. So here's an image from the Cosmic Background Explorer satellite of the Milky Way sort of as it cuts across the sky. Now, the Milky Way has globular clusters, which are small clusters of a few tens of thousands of stars. And these clusters form the halo around the Milky Way. There's sort of a sphere around the Milky Way of randomly orbiting stars. And in 1917, Harlow Shapley mapped the locations of the 93 then known globular clusters and found our solar system was not the center. Before that, people had thought we were roughly in the center of the universe because, well, when you look out, dust and gas block your view. So you get, the observed area had been roughly, like the earliest drawings of the universe were just the stuff close to us, basically. But in 1917, Harlow Shapley was able to map out and locate the center of our galaxy. And it found it to be about 30,000 light years from us. And the center of these globular clusters is about 28,000 light years away, and that's the nuclear bulge of the Milky Way galaxy. And at the center of that, there's a large black hole, Sagittarius A star. And Shapley correctly infirmed that our solar system was about 30,000 light years away from the center of the nuclear bulge. The Milky Way galaxy is about 100,000 light years in diameter, so 50,000 light years in 50,000 light years in radius. 22,000 light years thick is the thickness of the disk, while 20,000 light years is the thickness of the nuclear bulge. It's about 10 times the thickness of the disk. And beyond accumulating evidence, this is a little out of date. We know there's a massive black hole located at the core of nearly all galaxies' nuclear bulge. We definitely know there's one at the center of ours because we took a picture of it. But accumulating evidence suggests that there are massive black holes located at the core of basically all galaxies' nuclear bulge. Now, some very distant galaxies have very active black holes, and these are called quasars. Stands for quasi-stellar radio source, because they were radio sources that looked kind of like stars. They were bright points in the sky. But we knew they weren't stars because their spectrum didn't make sense. These are the most distant objects we've observed in the universe that are almost certainly the bright center. No, we know they're the bright centers of distant galaxies. They're from active galactic nuclei, where lots of material is falling into the black hole at the center of the galaxy. It gets incredibly hot, pumps out enormous quantities of energy. So one quasar is thought to be about 13 billion light years away. And considering the universe is only about, so they're all very far away. Most of them are more than 10 billion light years away. And the universe is only about 13.8 billion years old. 13 billion light years away is a long way away. They're the source of huge amounts of electromagnetic radiation. They're reasonably bright at a distance of 13 billion light years. They're ridiculously far away. And this larger release of energy is almost certainly due to material as it orbits and is drawn into the supermassive black hole at the centers of these galaxies. So this is quasar 3C273. It's thought to mark the location of a supermassive, about a 1 billion solar mass black hole. This is the first quasar we were able to figure out that it was super, super far away. It's the first one we got a distance on, I think. It's a little hard to remember because they all have names like that. But they measured the spectrum and realized the redshift was so enormous. So one of the aspects of when you look out into space, you're literally looking back in time. because it takes time for light to travel. Let me just mark the quasar. Oh. So the further we look out into space, the further we're looking back into time. Because it takes time for light to travel. So, if something is 10 billion light years away, the light has traveled for 10 billion years to reach us. So photographs taken today using light that may have left the star or galaxy thousands, millions, or even billions of years ago, depending on what you're looking at. So we can literally look into the past of the universe. We can look out and see back to as early as I think it's 380,000 years after the beginning of the universe. So something like 3.5 billion years into the past. So when we look at a quasar that's 13 billion light years away, that light left the quasar 13 billion years ago when the universe was very young. And most astronomers think the universe is around 13.7 billion years old. The exact date is a little iffy. There's actually some controversy on that right now because our current model of the history of the universe is starting to show cracks in a good way because we're finding out new things. So if we look at the galaxies around us, let me fix this. So the cluster of galaxies that our galaxy is in is called the local group. It's very imaginatively named. The local group is about 50 odd galaxies. That includes the Milky Way, Andromeda, and M33. Those are the three big galaxies in the local group. They're all within about 3 million light years from us. They're all gravitationally bound to each other. So any group of galaxies that is gravitationally bound to each other is called a cluster. So astronomers partition the universe into volumes or clusters of galaxies that range from about 3 to about 15 million light years in diameter. Clusters are all groups of galaxies gravitationally bound. They vary from small clusters like ours, which is only about 50, it's a little over 50 galaxies, to massive clusters that have thousands of galaxies. So the Virgo cluster has like a few thousand. I think the Coma cluster has almost 10,000. And clusters also group up. There's some structure of clusters. They're sort of organized. They sort of happen like strings on feeds on a string, or can be in groups. So you get superclusters, which are clusters of clusters. So we're part of the Virgo supercluster. So this is the local group of galaxies. Here are some of the nearby galaxies. There are 3 big galaxies. The Milky Way, the Andromeda galaxy, and M33, which is, I think, the triangulum galaxy as well. That's what it's called. And I think more than 30. This says it's a little out of date. It says 35 smaller galaxies. I think the total number of galaxies has gone up to like 50 odd. Let me just check that and oh, okay, more than 100. I'm gonna stick with the 50 now. We keep finding more. But the three big galaxies are Milky Way, Andromeda, and M33. And then 40 odd smaller galaxies. So, dark matter is the as yet unidentified. So when we look at galaxies, we find out that the matter we see is not enough to hold them together. They're literally spinning too fast for them to have a mass consisting of just the matter we see. And when we work out how much mass they should have, there's like a bunch of missing mass around the edges, basically. And if we look at clusters of galaxies, we can also see that they are also missing mass. And this is dark matter. We can work out there has to be some form of matter that has mass, that doesn't emit any light, and that basically only interacts through gravity. So this is but other than that, it's as yet unidentified. It's non-luminous matter in the universe. Analysis of the speed of revolution and the gravitational behavior of stars and galaxies indicates that galaxies and galaxy clusters contain a lot more matter than can be detected. And we've basically been able to entirely eliminate normal matter as a possibility. 90% of the matter can't be detected by any sort of wavelength of electromagnetic irradiation. And so it's postulated that the Milky Way galaxy is embedded within a sea of dark matter that could extend outward for 150,000 light years. And we don't know what dark matter is, but we've been able to eliminate some of these options. So these are some of the possibilities that were considered. On neutrinos, these are actually things that we eliminated. Neutrinos, unknown black holes, brown dwarfs, neutron stars, and other potential high mass material are possibilities for dark matter. Most of these have been eliminated, and the most likely possibility is some sort of exotic, massive, subatomic particle, basically WIMPs. So machos are massive compact halide objects. They're hypothetical, but possible contributors to the dark matter. However, we don't think they really are a major thing because we would have noticed them, basically. There's certain signatures they would have that haven't shown up. WIMPs, weakly interacting massive particles, are exotic subatomic particles. These are the most likely source of dark matter. We've never detected any. So there's a lot of wild guessing because the problem is all we know is that it's something that doesn't interact with electromagnetism. Maybe it interacts with the weak force, which is what WIMPs are. Maybe it doesn't. And we know it has to be above a certain mass. We've never found any in particle accelerators, which is where most of the search has been. They've never found any in any of their detection attempts, but all the detection attempts are built around assumptions about what dark matter is, and we know so little about it. It's sort of wild guessing. And here, oh, I forgot to do the thing. Let's, come on. Oh, stupid technical issues. Oh, I'm gonna try reopening this. There we go. Sorry about that. So this is a short video about dark matter and also doping.
The planets,
Oops.
moons, and stars make up less than 5.
So
The planets,
salt,
moons, and stars make up less than 5% of all the mass in the universe. The rest lies in the realm of absolute darkness. The dark universe is the invisible yet dominating component of the cosmos. It includes a substance called dark matter and a force called dark energy. While little is known about either, each helps us understand the universe beyond what the eye can see. Dark matter makes up about 25% of mass in the universe, but its composition is still unknown. The substance neither emits nor reflects light, and because of that, it cannot be seen. The existence of dark matter can be inferred based on its gravitational pull on the visible universe. According to some scientists, this force is what prevents stars within galaxies from drifting away. Dark matter may have also played a role in the creation of the cosmos. After the Big Bang, dark matter formed a network of filaments across the universe, and in this network, the first stars and galaxies were born. Not much is known about dark matter, but even less is known about dark energy. Dark energy is a mysterious force that fills the space between objects. It makes up about 70% of mass in the universe. Plus, it has a repulsive property that counteracts the force of gravity. The reason for dark energy's existence is unclear. One theory states that it's the fifth force nature. Yet another says it may help explain why the universe is expanding. In his theory of general relativity, Albert Einstein considered a repulsive force similar to dark energy that pushed space and particles apart. Called the cosmological constant, the variable may provide clues for the expansion of space and time. Much about the dark universe is left to be discovered, but with every theory and technological development, secrets of the invisible cosmos will come closer to being revealed.
So dark matter helps hold together galaxies. It's something, we're not exactly sure what it is. The study of the structure and the evolution of the universe is cosmology. So by looking at galaxies and looking at electromagnetic radiation from galaxies, astronomers can determine the structure of the universe. So from work accomplished so far, most galaxies occur in clusters and linear filaments. The biggest structure we've observed is known as the Great Wall, which is around, I can't remember a few hundred megaparsecs. So several hundred million light years across. And that's sort of the biggest scale of structure in the universe. Bigger than that, we see everything is much of a muchness. So one of the things about the universe is that it is expanding. This was discovered by Edmund Hubble after he figured out that there were other galaxies that are own by observing Andromeda initially and figuring out and measuring the distance to it and figuring out it was made of many stars. He examined the spectrum shifts of various galaxies, and he discovered that the further away galaxies were, the faster they were moving away. He noticed that some shifts were blue, some shifts were red, but all the blue shifted ones, which would correspond to the galaxy moving towards us, were all in our local group. They were all close to us. Roughly. The red shift indicates galaxies that are moving away from us. Galaxies moving away from us, almost all galaxies in the universe are moving away from us. And it turns out he found a correspondence with the way that these were moving away. The further away a galaxy was, the faster it was moving away from us. He noted that far away galaxies all exhibited red shifts, and he also noted the further away the galaxy, the larger the red shift. And he actually found a relationship. There's a linear relationship where there's a number, you can multiply the distance that a galaxy is away from us to find out how fast it's traveling away from us. It's called Hubble's constant. It's a linear relationship. So if a galaxy is twice as far away from us as another galaxy, it will be moving away from us twice as fast. So Hubble concluded the universe had to be expanding. So here's a video about the expanding universe.
The universe is getting bigger every day. And what we understand now is that the amount it's getting bigger is getting bigger every day. The expansion of the universe is accelerating.
As far as we know.
Ironically, what this means is that as time goes on, even though the universe is getting bigger, we see less of it.
How is the universe getting bigger? Finding the answer has become one of the greatest quests in modern science.
Just a few years ago, we were trying to measure how much the universe is slowing down over time. It makes sense, right? An explosion happened a long time ago, the Big Bang.
Scientists assumed the Big Bang would slow down and gravity would pull things back together. But that's not what they were seeing in the cosmos.
Astronomers think that the universe appears to be expanding at an accelerating rate.
Now, we have no idea what's causing this, so I'll let you in on a secret here. Whenever astronomers don't know something, they tend to say dark energy.
Even though scientists are baffled, they know this thing called dark energy makes up 70% of what's out there in the cosmos. It's stronger than gravity, and may eventually be stronger than the forces that hold atoms together.
My body is held together by the electromagnetism in my atoms. But what if the expansion of space increases and accelerates, and it even overcomes those forces? Astronomers are calling that the Big Rip. And although we don't know this will happen, it's a possibility that eventually the expansion will get strong enough to rip apart atoms, to rip apart our very bodies. Even matter will fly apart.
One way to wrap our brains around the expanding universe and the Big Bang is to use an analogy. For instance, tennis balls on a piece of elastic. Here, each tennis ball represents a galaxy. So this one could be our own Milky Way galaxy. And the elastic is space itself. Now, since we know the universe is expanding, it's like taking this elastic and stretching it. Now, as the elastic expands, the galaxies start to spread out and get more and more remote from one another. So our simple model of the universe with tennis balls and elastic literally breaks down if we try to apply it to one ruled by dark energy. Because if we're trying to show a universe in which the rate of expansion between the galaxies is actually accelerating over time, our elastic would have to stretch infinitely far, and we would have to run away from each other infinitely fast. Now, we can't do that with a simple model, and that, in a way, is an example of just how bizarre a dark energy-dominated universe could be.
So Hubble's law is that the universe is expanding, and the greater the distance, the greater the recessional velocity. This can be calculated from the observed redshift. And the slope of this line, so we have distance, this is in megaparsecs, and this is recessional velocity in kilometers per second, is Hubble's constant. So the recessional velocity is equal to the distance in megaparsecs times Hubble's constant. So Hubble's law says the greater the recessional velocity of a galaxy, the further away the galaxy is. So this is saying that, the recessional velocity of a galaxy is equal to Hubble's constant times the distance to that galaxy. But if you sort of run this backwards, well, if everything's going away at this expansion rate, well, we can run this backwards and everything would have all been in the same place at a time that is 1 over Hubble's constant, basically. So you can calculate the age of the universe based on Hubble's constant. If you want it in years, if Hubble's constant is in kilometers per second per megaparsec, you take 9.78 times 10 to the 11 and divide it by Hubble's constant in kilometers per second per megaparsec to get a rough estimate of the age of the universe. Actual calculations of the age of the universe have some corrections for changing rates of expansion. And there are 2 separate ways of doing this. And they come up with different numbers and they're not being resolved. This is actually where that big crisis in astronomy is right now is coming from. It's called the Hubble tension. Because we were hoping that new observations would like fix this issue, and they didn't. They made it worse. So what does it mean if all the other galaxies are receding away from us? Does this mean we're at the center of the universe? No. It means that everything is expanding and the space in between everything is expanding. So from everybody's point of view, everything is traveling away from them. Pretty much all astronomers agree we live in an ever-expanding universe. The debate is not whether it's expanding and will continue expanding. It's whether that expansion is speeding up or slowing down. That's the big debate right now. And more how fast it's speeding up or slowing down. Because it looked like it was speeding up, and then our calculations about the rate at which it's going are starting to fall apart. And therefore, every galaxy is receding away from every other galaxy. This is wholly accepted. And so an observer from anywhere in the universe would witness the same phenomena, receding galaxies. The classic example for explaining this is the raisin bread example. I don't know why it's always raisin bread, but it's always raisin bread. So the idea is that if you have a loaf of raisin bread and it's raising, all the bread expands. And that means the distance between all the raisins increases, and it increases more the further apart they are. So if it doubles in size, the distance between all the raisins will double in size. So the further apart the raisins were, the bigger the change was, so the faster they recede. The greater the initial distance from any given raisin, the faster and further the other raisins move. But there's no, well, raisin bread has a center, but as far as we know, the universe doesn't. So if we wanted to calculate the age of the universe, we could do a rough calculation. If the constant rate of expansion of the universe is 71 kilometers per second per megaparsec, the age is going to be 9.78 times 10 to the 11 divided by the Hubble constant. So 9.78 times 10 to the 11 divided by 71 gives us an age of around 13.8 billion years. But if the Hubble constant was instead only 50 kilometers per second per megaparsec, the universe was expanding more slowly. The universe would actually be older. So the age would be 9.78 times 10 to the 11 divided by 50, which would be 19.6 billion years. So early theories expected that gravity would eventually slow down the expansion. There was some debate whether there was enough stuff in the universe for it to come to a stop and recollapse, or if it would just continue expanding because gravity wouldn't be enough to bring it to a stop. But recent evidence points towards the universe expanding forever. In fact, recent data suggests that the expansion is actually accelerating. And the solution to this, we created this idea of dark energy to explain this acceleration. This is where all the debate right now in astronomy is going on. So there's some debate about what's going on with dark energy and the future of the universe. We have a better understanding of the past of the universe. It's not perfect, but we have a better understanding. So while the galaxies are moving away from each other at the present time, they must have been closer together in the past. So the universe must have been much more compressed. And in fact, most astronomers think the universe began as a small, hot, extremely dense entity that rapidly expanded and sort of exploded outwards about 14 billion years ago. That's the Big Bang. So the universe started super hot and dense. For a short period, it started to expand. There's a short period known as inflation that we think happened that solves a bunch of issues we can with what we know about the universe. It ensures the universe has certain properties. It smooths things out a bit. Then the universe continued to expand and cool and form the universe. That's the Big Bang. Yeah. So here's a short video about the origins of the universe. And the Big Bang.
The universe is everything, from the tiniest particles to the largest galaxies to the very existence of space, time, and life. But how did it all begin? The origin of the universe is the origin of everything. Multiple scientific theories, plus creation myths from around the world, have tried to explain its mysterious genesis. However, the most widely accepted explanation is the Big Bang Theory. The Big Bang Theory states that the universe began as a hot and infinitely dense point. Only a few millimeters wide, it was similar to a supercharged black hole. About 13.7 billion years ago, this tiny singularity violently exploded. And it is from this explosion, this bang, that all matter, energy, space, and time were created. What happened next were two major stages of the universe's evolution. Called the radiation and matter eras, they're defined by key events that helped shape the universe. First came the radiation era, named for the dominance of radiation right after the Big Bang. This era is made of smaller stages, called epochs, that occurred within the universe's first tens of thousands of years. The earliest is the Planck epoch. No matter existed in the universe at this time, only energy and the ancestor to the four forces of nature, the superforce. At the end of this stage, however, a key event occurred in which gravity split away from the superforce. Next came the Grand Unification epoch, named for the three remaining unified forces of nature: This epoch ended when one of those forces, called strong or strong nuclear, broke away. Then, the inflationary epoch began, during which the universe rapidly expanded. Almost instantly, it grew from the size of an atom to the size of a grapefruit. The universe at this time was piping hot, and it churned with electrons, quarks, and other particles. Then came the electroweak epoch, when the last two forces, electromagnetic and weak, finally split off. During the next stage, the quark epoch, all of the universe's ingredients were present. However, the universe was still too hot and dense for subatomic particles to form. Then, in the hadron epoch, the universe cooled down enough for quarks to bind together and form protons and neutrons. In the lepton and nuclear epochs, the radiation era's last two stages, the protons and neutrons underwent a significant change. They fused and created nuclei. And in doing so, they created the first chemical element in the universe, helium. The universe's new ability to form elements, the building blocks of matter, cued the matter era. Much as the name suggests, the matter era is defined by the presence and predominance of matter in the universe. It features three epochs that span billions of years, the vast majority of the universe's lifespan, and includes the present day. The first was the atomic epoch. In this stage, the universe's temperature cooled down enough for electrons to attach to nuclei for the first time. Called recombination, this process helped create the universe's second element, hydrogen. This hydrogen, along with helium atoms, dotted the universe with atomic clouds. Within the clouds, small pockets of gas may have had enough gravity to cause atoms to collect. These clusters of atoms, formed during the galactic epoch, became the seedlings of galaxies. Nestled inside those galaxies, stars began to form. And in doing so, they cued the latest and current stage of the universe's development, the stellar epoch.
I wouldn't trust them.
The formation of stars then caused a tremendous ripple effect and helped shape the universe as we know it. Heat within the stars caused the conversion of helium and hydrogen into almost all the remaining elements in the universe. In turn, those elements became the building blocks for planets, moons, life, everything we see today. This ecosystem of everything was only possible because of the many stages in the universe's development. While countless questions about the origins of our universe remain, it's only a matter of time for some long-sought answers to emerge.
So, with our current understanding of subatomic particles and the structure of the universe, we can extrapolate to about 10 to the minus 43 seconds after the Big Bang. That is a very short period of time. So initially, the universe was filled with radiation. And within the first 4 seconds, protons, neutrons, and electrons formed. We went through all those earlier epochs. Hydrogen and helium nuclei, helium nuclei, hydrogen protons fused to form helium nuclei around, that process finished at around 5 minutes, so within the first 3 minutes. It's called recombination, which is a terrible name, but the universe became transparent when atoms actually formed about 380,000 years after the Big Bang, and after about maybe 500,000 years, gravity started to be, we're not exactly sure when gravity started forming galaxies and stars, but it was very early. 500,000 years is probably the beginning of that process, yeah. So, and then the first stars and galaxies formed had formed by a few hundred million. We've observed galaxies from only a few 100 million years after the Big Bang. So experimental evidence supports the Big Bang in three major areas: the cosmological redshift. The galaxies today all have a redshift in their spectral lines. The cosmic microwave background. This is literally the echo of that point when atoms formed and the universe became transparent. So the light from that stage, when a light stopped constantly interacting with all the matter, flowed out, and we can still see it. We can see that fireball from the Big Bang cooled down as the universe expanded as the cosmic microwave background. So if you look in any direction, you will see microwave radiation. It fills all space and represents the redshifted glow from the Big Bang. And then the helium to hydrogen ratio, the hydrogen to helium ratio of 3:1 in the stars and all interstellar material matches up with our models for the nucleosynthesis period in the Big Bang. And without a doubt, our current knowledge of the formation of the universe is incomplete. In 1980, for example, the standard model of our origin of the universe was modified. The inflationary model adds this extra step, short period of rapid inflation, as the strong force, after the gravity had disconnected from the strong force, but in this sort of grand unified era, where the universe consisted of a large number of separate regions that formed in about 10 to the minus 35 seconds. Oops. Let me fix this. There. And so our region is thought to be basically a bubble that rapidly expanded by a factor of about 10 to the 50 in a very short period of time. And this resolves some of the issues in our observations, where if we look in opposite sides of the universe, if with the original standard model of our origin of the universe, we see opposite sides of the universe that were too far apart to have ever come in thermal contact, look like they were in thermal contact with the same temperature, basically. And the universe is also too flat, kind of. But a rapid period of expansion solves both of these problems because everything was closer together very early on. So things could have been in thermal contact, and that expansion stretched everything out and flattened everything out. So it's thought that, we had quantum fluctuations, a period of rapid inflation very shortly afterwards, which locked in those quantum fluctuations at about 380,000 years. We have the afterglow light pattern from the separation. The first stars are maybe 400 million years into the age of the universe. Actually, probably earlier. We keep finding earlier ones. So there's sort of some estimations here. So somewhere in this period, the first stars happened. There's a period called the Dark Ages, which is actually a really good name because it was literally dark. And then we had the domination of, the development of galaxies, planets, etc. And then at some point, dark energy probably started to dominate, and we had accelerated expansion. So if the inflationary model is correct, the entire universe, beyond our universe, is so enormously huge, it's really hard to understand. And the portion we can observe is only a tiny fraction of the whole. And at the present time, the inflationary model is our best theory to explain the origin of the universe. But also at the present time, our understanding of how the universe expands is currently in massive conflict over something called the Hubble tension. So our current model is actually starting to fall apart. So, I mean, sort of. And that's the end of chapter 18. The universe is the totality of all matter, energy, and space. The huge imaginary sphere on the sky in which all the stars seem to be located is the celestial sphere. The path the sun takes across the background of stars is the ecliptic. A parsec is the distance, 3.26 light years, to an object with a parallax of 1 arcsecond. The layer of the sun that we see is the photosphere. Luminosity is a measure of the, apparent bright magnitude is a measure of the brightness of a star as seen from Earth. So that's apparent brightness or apparent magnitude. Absolute magnitude is a measure of the brightness of a star if it were seen from a standard distance of 10 parsecs. So absolute magnitude is a measure of how actually bright a star is. Apparent brightness or apparent magnitude is how bright we actually see it from Earth. So apparent magnitude is affected by distance, absolute magnitude to the star, absolute magnitude corrects for that. We can also talk about the luminosity of the star, which is just how much energy it pumps out. The HR diagram plots stars' absolute magnitudes versus the temperature of their photosphere. The band of stars from the upper left to the lower right on the HR diagram most stars fall into is called the main sequence, which corresponds to the longest portion of a star's life, where it's fusing hydrogen into helium. Relatively cool, bright stars with diameters of 10 to 100 times that of our sun are the red giants. These are stars that have run out of hydrogen in their cores and have started the end of their lifespan. The small, hot, dim stars left behind by the death of low-mass star are called white dwarfs. So these are basically the corpses of stars. Nebula are cool, denser clouds of interstellar gas and dust. These are what form new stars. The shell of gas ejected from an old low-mass star is a planetary nebula, called because it's roundish and people thought it was planet-looking. It was the 17 or 1800s. So a white dwarf star that suddenly increases dramatically in brightness for a brief period of time is called a nova. When a star explodes, it's a supernova. Other than hydrogen and helium, all of the elements up to iron are thought to be made during normal fusion processes in stars of various masses. There are some subtleties to that, but it doesn't matter for the purposes of this class. But there are some subtleties to that. All elements heavier than iron are made in supernova explosions, or at least our supernova explosions are required. Some of them actually require additional steps. Again, the actual formation of all elements is kind of complicated, but in general, up to iron can be made in normal stars. To go past iron, because you don't gain any energy fusing past iron, you need the massive release of energy of a supernova explosion. A neutron star is the extremely dense remnant of a high mass star that's made of neutrons. A rapidly rotating neutron star that appears to pulse on and off is called a pulsar. A black hole is an object so dense that not even light can escape from its surface because of the object's intense gravitational field. A large gravitationally bound collection of stars and gas is a galaxy. Galaxies come in 3 types: spirals, ellipticals, and irregulars, though in order of commonness, ellipticals, spirals, and irregular. Ellipticals are the most common. A globular cluster is a spherical collection of hundreds of thousands of gravitationally bound stars, usually found in the outlying regions of a galaxy. The additional mass required to keep galaxies gravitationally bound that we can't see is called dark matter. The study of the structure and history of the entire universe is called cosmology. Hubble's law says the further away a galaxy is, the faster it is traveling away from us. The force accelerating the expansion of the universe, as far as we know, is called dark energy. The universe is expanding because space itself is expanding. The Big Bang theory of the beginning of the universe states that the known universe was smaller, hotter, and denser in the past, and then it began rapidly expanding around 13.8 billion years ago. The echo of the beginning of the universe that provides evidence of the above theory is the cosmic microwave background. And in the very early universe, hydrogen and helium are created in a ratio of 3 to 1. So the universe is about 75% hydrogen and about 25% helium. And then everything else is less than 1%. So that is the end of chapter 18. I'm going to go over the announcements again. So the chapter 18 homework is due on Monday, the 8th. The chapter 18 quiz will be on Monday the 8th in lecture. So on Monday, we'll do review of chapters 16, 17, and 18 and the quiz. Because I don't want to make you take the quiz today after I just finished it in SI. And I don't want to make you take the quiz for chapter 18 on the same day as the test next week. So working that out, it ends up in lecture on Monday. On Monday in lecture, I'll do review and the quiz. The exam on number 3 on chapters 16, 17, and 18 will be on Wednesday, the 10th. And then please turn in any labs you haven't turned in. You can do that in class or outside my office, which is room 335 down the end of the hall. That's all I wanted to cover for today. I'll see you all next week. Yeah. Any questions about anything? If not, have a nice day.